An average, ordinary person, whose whole knowledge of the universe comes from science fiction movies, thinks of a black hole as some kind of cosmic monster that sucks everything upon its first encounter. Hello everyone! By the way, how come there are so many black holes in the universe and they have not swallowed up the entire universe? Have they, in fact, already swallowed up, or will they do so in the near future? Welcome to our channel everyone! This video will make it all clear. Sounds interesting? Well, let's get started. A place where if you go there, you will never come back. There are many different types of black holes, but they all have one thing in common. As soon as you fall inside the event horizon, nothing can escape the gravitational trap. No particle, no wave, not even light can do so. Why? Because at a point below the event horizon, it takes a speed greater than the speed of light to overcome the gravity of a black hole. What would happen if you stood on the surface of the Earth and fired a pistol into the sky? The bullet would gain altitude but would eventually descend, because the bullet does not have the speed to overcome the Earth's gravity. For the bullet to begin orbiting the Earth without falling, it would need a speed of 7.91 kilometers per second, and for it to completely overcome gravity and fly into space, it would need a speed of 11.186 kilometers per second. These speeds are called the first and second space velocities on Earth, respectively. It is the mass of an object and its radius that determine the space velocity. The greater the mass and the smaller the radius, the greater the velocity must be to overcome the gravitational force of the object. It also depends, of course, on distance, making takeoff from the surface of the Earth more difficult than starting from an orbit away from the surface. A black hole does not have a surface like other celestial bodies, but instead has a singularity. There is one point of concentration of very small, yet tremendous mass, as if poked with the point of a needle. Thus, the velocity of the universe in the region around such a point exceeds the speed of light. The boundary of this region is none other than the event horizon, which looks like the surface of a black sphere. All things that fall beyond the event horizon have no way back, because nothing exceeds the speed of light. It just keeps falling to the singularity. The above is a very simple explanation at textbook level. In our videos, we do not use difficult quantum mechanics formulas, because if we do such a thing, you would fall asleep behind the screen. Nevertheless, it does clarify the eerie nature of the black hole, the monster of the universe that exploits the laws of physics to take possession of all matter. As the universe is not empty at all, every black hole will always have something falling into it, be it dust, gas, or a small meteorite. On occasion, something large, such as a star, may fall. All falling objects, without exception, increase the mass of the black hole. In other words, every time a black hole swallows cosmic dust, it grows. This feature of a black hole is perhaps more frightening than the inability to return from the event horizon. Even if you were to relax in the orbit of the black hole, secure in the knowledge that you are safe from the distance, the demons of the universe would sooner or later inflate the eerie black sphere, incorporating enough mass. All that awaits you is doom. After that happens, the black sphere would just keep getting bigger and bigger. Empty will save you. If you know what we know so far, you may want to ask, then why are we still alive like this? Have we not been swallowed by a black hole? In the traditional view of the universe, widely shared in the late 20th century, the answer to this question was surprisingly simple, because the universe is big. Consider the typical formation process of a stellar mass black hole. Here is a single star. After a month or so, it cheerfully exploded into a supernova and ended its life. The central core gravitationally collapsed and became a black hole. Now, it wants to grow to the point where it could eat matter from outside its own stellar system, but where would it get the matter necessary to do so? In fact, the mass of non-stellar objects in a stellar system is very small compared to the mass of the star itself. For example, the entire solar system combined has less than 1% of the mass of the Sun itself. Black holes are, in fact, very compact objects. According to our current knowledge, the Sun would never gravitationally collapse into a black hole. But if all the researchers on Earth were wrong and that were to happen, the radius of the event horizon of this little black hole would be only 3 kilometers. The supermassive black hole at the center of our galaxy is about 4 million times the mass of the Sun, but in contrast, it is completely small in size, not even the radius of Mercury's orbit. Next, let us look at the size and distance in space. The average distance between the Earth and the Sun, 1 astronomical unit, is a little less than 150 kilometers. This is a little more than twice the longest distance between the Sun and Mercury. The distance from the solar system to the nearest star, Proxima Centauri, is 4.244 light-years, or a little longer than 268,395 AU. When an object of a certain mass collapses gravitationally into a black hole, an event horizon is formed, the radius of which is called the Schwarzschild radius. Even for a celestial body with a mass equal to the total mass of the galaxy, the Schwarzschild radius is only a quarter of a light-year long. Think about it and you will understand. For a black hole to extend over a distance of 4.2 light-years, the distance to our solar system's neighboring stellar system, it would have to have the mass of the entire Virgo supercluster combined, which contains at least 100 galaxy groups or clusters, and extends over a diameter of about 200 million light-years. Not a single gravitationally collapsed star has such an enormous amount of material around it. The universe is, after all, completely empty. All any black hole can do is to gape hungrily at the delicious-looking matter in the faraway stars. Why are we still alive? Now, we think we have answered why there is still no single black hole that has swallowed the entire universe, and whether or not there is a possibility of such phenomenon in the future. There is, however, another problem with black holes and the Schwarzschild radius. As you, the astute viewer, may have already guessed. The Schwarzschild radius of a black hole, with the combined mass of all the objects in the observable universe, is 13.7 billion light-years, the length light must travel from the birth of the universe to the present. However, we know from the Big Bang Theory that the entire universe was much smaller than it is today. For example, until about 10 seconds after the Big Bang, the observable universe was small enough to fit in our solar system. Now, after a mind-boggling amount of time, the universe is much, much larger than the Schwarzschild radius of 13.7 billion light-years. Why didn't the universe collapse gravitationally and shrink? The conditions were seemingly all in place. Because enormous masses were squeezed into minuscule space. Isn't there any contradiction in the Big Bang Theory in this respect? This is one of the difficult problems in modern cosmology. Researchers believe that it was the tremendous rate of expansion that held back the collapse of the universe in its early stages. It was many times faster than the speed of light. Space itself was expanding, and because each piece of matter was, on average, at rest, it was able to exceed the speed of light. It is difficult to imagine this state without being armed with equations, but let us imagine it as an ice floe floating on a river. The ice mass itself is not trying to move, but the distance between the ice masses is widening as the river current carries it along. This concludes this video. Thank you all for watching. We hope you have enjoyed it. We are apparently incredibly lucky. Even if the speed of expansion had been so dizzyingly fast at the beginning of the universe, it would have collapsed instead of expanding if it had been even a tiny fraction of a decimal place slower. How did we get so lucky? This is the question that stands in front of those who pursue the truth. Can you answer? Please let us know in the comment section. We always enjoy reading your comments. Goodbye for now. Please don't forget to subscribe to our channel, like us, and share us on social networking sites. See you again soon. Bye!